Greetings everyone. Welcome to Conf42 Observability 2025. My name is Vamsi Praveen Karanam, a senior software engineer who focuses on cloud-native automation and large-scale data processing pipelines. Our topic is adaptive parallelism insights, which I'll abbreviate as APIX after this introduction. APIX combines open standard telemetry with a compact graph neural network so that an AWS step function workflow can learn to tune itself while it is running. By the end of this session, you will understand three things. First, how we capture branch level data without rewriting business code. Second, how a small model converts that data into useful guidance. And third, how a closed loop safely applies the guidance to reduce latency and cost while keeping every decision auditable. To begin, serverless fanouts offer near instant elasticity, yet three problems surface as scale grows. First, latency cliffs arise because a few slow branches delay the entire workflow. Even a single hotspot can push the entire service level agreement. Second, tracing gaps appear because high-level dashboards average away branch-specific anomalies, which means engineers cannot pinpoint trouble quickly. Third, cost spikes emerge when hidden retries, cold starts inflate the monthly bill without obvious warnings. These pains led us to frame three guiding questions. Question 1 asks how to collect fine-grained telemetry from every branch while adding minimal overhead. Question 2 considers whether a lightweight artificial intelligence model can digest that stream quickly enough to make timely recommendations. Question 3 asks how to apply those recommendations during a live run without breaking concurrency limits or financial guardrails. The rest of the talk answers each questions in turn. Contextually, many enterprise workloads such as data enrichment, ETL retries, and compliance redaction depend on the map state pattern inside AWS step functions to fan out tasks. Limitations acknowledge the native execution history application programming interface shows only course events, which hides branch behavior that matters. Standardization helps because OpenTelemetry, the leading vendor neutral format for traces, metrics, and logs, let us instrument once and analyze anywhere. In parallel, CloudWatch EMF embedded metric format adds structured counters inside Lambda logs without agents. Research to date often targets virtual machine clusters with reinforcement learning. Less focus has landed on dynamic state machine graphs, where topology changes every minute. Opportunity identified. Graph neural networks excel at reasoning over graphs whose nodes and edges evolve rapidly, so they fit our fan-out scenario. APIX, therefore, unites detailed telemetry, open standards, and a compact graph neural network into one practical closed-loop control system. The picture at right shows the flow of data and control. Starting at the top, the instrumentation layer adds an open telemetry span to every task. Parallel and map branch spans a carry chunk ID and the same wrapper logs counters such as payload bytes, retry count, cold start time by using CloudWatch embedded metric format. Next, the telemetry pipeline sends spans over the OpenTelemetry protocol to a collector running on AWS Fargate. The collector passes real-time streams into Kinesis data file host, which fuels live dashboards in Amazon managed Grafana, and it also stores raw records as Parquet files in Amazon Simple Storage Service for deep analysis. Moving downward, SageMaker Serverless hosts a two-layer graph neural network with about 1.2 million parameters. Every 60 seconds, the model consumes the latest window of branch metric and predicts an ideal chunk size, plus confidence and projected cost and latency impact. EventBridge then delivers that inference to a Lambda callback. The callback applies guardrail checks and, if they pass, patches the running map state through the step function update application programming interface. Finally, governance is preserved because each inference has hashed, stored in systems managed parameter store, and echoed into subsequent spans, giving auditors a full lineage from decision to outcome. Automation must be safe, so the controller enforces three boundaries before any change. First, the chunk change window limits adjustment to 25% within 5 minutes, which prevents oscillation. Second, the concurrency cap ensures the new chunk size keeps total lambda concurrency below the account quota minus a safety buffer retrieved from parameter store. Third, the rollback trigger monitors 95th percentile latency and throttle errors. If both rise for 2 consecutive windows, the controller reverts to the prior chunk size. Together, these safeguards let the model explore improvements while guaranteeing that production stability and cost limits remain intact. We measure first because insight depends on data quality. Span emission adds about 2 milliseconds per invocation, a negligible overhead for data processing tasks that often run for seconds. After capture, the open telemetry collector batches spans, pushes them to Kinest's data file host, and writes fully fidelity records to Amazon S3. Visualization follows, where managed Grafana converts those streams into live heat maps, highlighting slow or throttled branches within seconds. Flexibility matters, and because every interface follows open standards, teams can replace Grafana with another dashboard or route Parquet files into S3 for any analytical platform or without revisiting application code. Experience shows that this separation accelerates debugging and gives finance teams precise cost attribution tied to trace identifiers. Evaluation used 3 workloads. Synthetic uniform contains 10 terabytes of uniformly sized 1 megabyte records. Synthetic skewed SS also spans 10 terabytes but injects 5% larger records up to 10 megabytes to force slower processing. Live enterprise entity data, for example, like contractual data, represents 3 terabytes of anonymized production updates. Baseline compared were static patching at 1000 items, dynamic subtree partitioning that splits branches above 2 gigabytes, and A PIX adaptive chunking. Metrics tracked include 50th, 90th, and 95th percentile latency, absolute cost in United States dollars, and throttle error counts. Reading the table, adaptive chunking shows the lowest latency across all the percentile and the lowest cost for every workload. For synthetic skewed, throttle errors drop from 47 under static patching to 5 under A PIX, demonstrating resilience against uneven record sizes. Live enterprise data follows the same trend, with adaptive chunking cutting both tile latency and cost while reducing throttles from 24 to 3. In summary, real tuning delivers consistent performance gains and tangible cost savings. 5 lessons for anyone who wants to replicate A PIX. First, sample generously, capturing every span during peak windows so retry storms are visible, downsample later to trim storage if needed. Second, activate guards. The 25% cap on chunk changes smooths workload burst and prevents oscillation. Third, connect costs. Publishing dollar deltas alongside trace identifiers quickly gained trust from finance stakeholders. Fourth, inspect retry patterns. Since high retry counts often pinpoint hard partitions or downstream rate limits, pairing retry count with chunk identifiers made those hotspots obvious. Fifth, retrain weekly, because as new entity types enter production, the graph neural network must adapt to maintain prediction accuracy. Collectively, these practices turned A PIX from prototype into a production service adopted by multiple teams. Every study has limitations. Cold start variability persists even with snap start. Residual jitter can influence tail latency and may exaggerate gains. Synthetic bias is possible because synthetic workloads, while realistic, may overlook extreme traffic patterns found in the wild. For future work will replay full production traces to close that gap. Model drift remains a risk. Shifting data distributions can erode predictions quality, so automated drift alerts trigger retraining when error crosses a personal threshold. Recognizing these limits helps others decide whether APIX fits their environment and guides our roadmap for continued validation. In closing, adaptive parallelism insights turns detailed telemetry into timely recommendations that update step functions workflow safely. Benefited delivered, teams gain faster executions, lower compute bills, and complete audit trails without changing business logic. Next steps, we intend to coordinate turning across multiple workflows that share concurrency limits and explore WebAssembly-based span features extraction to reduce overhead even further. Appreciation. Thank you for your attention. Your questions and feedback through conference forums are welcome. And I look forward to hearing how you apply adaptive observability in your own pipelines. Thank you.